cohomology of arithmetic groups will return with Frank Calegari's lectures.
So thank you for the invitation. These talks are in some sense a sequel to the talks by Professor Speh, although they're concentrating on a sort of different phenomenon. Rather, instead of the cohomology and characteristic zero, the cohomology integrally, and in particular the torsion cohomology. Okay. So I want to begin by talking about a lesson that we've learned from previous lecture series, which is that namely given a modular curve or given a Shimura variety, it's often useful to consider all the levels at once. So in some sense, this was the principle maybe first, maybe even going back to Gelfand, which is to introduce representation theory. Representation theory. But the representation theory already, in terms of what we've seen, has come in two somehow quite different flavors. So I just want to remind you about them. So the first one, so here's two flavors. So one is maybe representations, and let me say, just stick to GL2 for a moment, of GL2QP. So how do these arise? Well, what we can do is we consider, say, a modular curve. We can look at its cohomology, and we can take the modular curve of level p to the n, say with coefficients in C. So this modular curve, well, what is it? In fact, this modular curve, the same symbol is used to denote two different things. Already this came up in Showu's talk. So on one hand, even just as a complex manifold, on the one hand, you can think about it as a moduli space of elliptic curves with a basis for their p to the n torsion. So that's a very nice space. On the other hand, you can think about a quotient of the upper half space by a congruent subgroup of SL2. And they're different. As we saw in Showu's talk, the moduli space, if you think about a pair which is a basis for the p to the n torsion, you can consider the Weil pairing. And the Weil pairing, well, that will just be a p to the nth root of unity. And certainly if you vary the elliptic curve analytically, this will remain constant. So if you think about it in the moduli theoretic terms, you get a disconnected union of curves, whereas if you consider the quotient of the upper half plane, of course, you'll get something connected. So this makes a difference also in Kai Wen's talk. We're talking about components and Shimura varieties versus just purely these abstract objects. And, well, sometimes you want one and sometimes you want the other. One reason for wanting the disconnected components is that it helps and is more natural as far as the group theory is concerned. So in particular, that's the one I'll take. And what it means is that this will have an action of the group GL2 Z mod p to the n Z. If you had just taken the quotient of the upper half plane, you would have SL2 instead. But now also the center is acting somehow on the components, and it's good to remember that. Okay. So now we can take, for example, the direct limit of this object. And well, all these groups will act for larger and larger n. And so we'll end up with a representation of GL2 ZP. So far, so good. But again, the point about these objects, they have these extra hecasymmetries, and the hecasymmetries exactly amount to the fact that this upgrades to an action of a somehow much more interesting group of GL2QP. Okay. So this is a story that is somehow quite classical, and it's a story that already is something you can start to talk about when you replace C by, say, a finite field of characteristic P or characteristic L. So what might differ in that case is, well, you have the same group, but now you're looking at a representation in different fields, and that representation theory can be more complicated when you have different phenomena in finite characteristic than it does in characteristic zero. But it's still, in some sense, the same kind of game, and you might try to generalize the same kind of tools that you saw before. Okay, so this is somehow one flavor, but I want to also mention a second flavor, which was somehow behind what Birgit was saying in her talks, which is related to the representations not of GL2QP, but rather somehow of GL2R. Okay. So, well, without saying too much, about what was going on. I mean, what was somehow the idea behind her talks? You're looking at the cohomology of some curve, or more generally, maybe some compact Shimura variety, or even more generally, some Shimura variety with a boundary. You want to understand its cohomology. So if you have a compact manifold, you can instead consider its de Rham cohomology. And now if you have, say, a compact manifold, you can understand its de Rham cohomology by maybe trying to represent classes by harmonic forms. Okay, in other words, you can use some kind of analysis. And the way that sort of manifested itself in her talks, well, you have representations of GL2R in some sort of very naive way, but ultimately when you tried to compute the cohomology, you ended up looking, instead of representations of this group, but rather you somehow took a derivative of this action and look at representations maybe of a Lie algebra instead. You look at GK cohomology. And so what does this somehow involve? This somehow involves having functions and taking maybe the derivatives of this action and ending up with some kind of differential operators that you're trying to understand. For example, in the classical case of modular curves and modular forms, you have a modular form, it'll generate some representation. But when you start looking at the action of these differential forms, you'll have these level raising and level owing operators from the Lie algebra of GL2. And maybe, I mean, what type of operators are there? I'm saying they're differential operators, but maybe explicitly the specific modular form, if you look at what it means to be a representation, say, of discrete series, you'll see that there'll be a particular element that will be annihilated by certain operators, which will amount to the Cauchy-Riemann equations. So if you take some discrete series, you'll find there's a particular vector which, in terms of its representation, will satisfy a differential equation. That will mean it's actually holomorphic, which is why you get holomorphic modular forms. And this picture here is really somehow going to be completely absent when we start replacing C by FP, because there's not really an analysis in finite characteristic. So this is in some sense bad news. In some sense it's also good news, because it means that the methods are somehow much more elementary. So that means that my talk is really going to be, in some sense, much more basic than some of the previous talks, in that the initial tools that you have to start thinking about these objects are really almost just coming from algebraic topology. Okay. So this is somehow an introduction. So what I want to talk about, first of all, is just the general concept of towers. So towers of manifolds. So let me first give you some examples of what I have in mind when I say towers. So perhaps the kind of example is, if we consider the modular curve, then you consider these covers by modular curves of full congruent subgroup for higher and higher levels. And so on. You consider these all together. So, I mean, this is some kind of sequence of objects. And in mind, you have thinking about constructing from this sequence maybe a limit of cohomology groups that will have an action of some interesting group. Okay. So this is a tower. But let me give, so maybe this is, say, example 0. But let me also give some much more basic examples of towers. So instead of modular curves, let me consider the following tower. So let me suppose that M is just the circle. So the fundamental group is just Z. So the finite covering spaces are coming from finite quotients of Z. So, well, of course, here I could have, instead of putting powers of P, I could try to have all levels at once. But this usually breaks up into a story in which we consider one prime at a time. So let me also do it in this case. So, well, what are the covers I get? If you take a quotient, which is Z mod P to the NZ, you get a covering of S1. What's the covering space? It's just S1. So here I just, let me somehow draw it like this. Here's M. This is a small circle. And then I'm getting bigger and bigger circles. So M1, M2, just giving by winding itself around P times. So this is somehow again a tower of manifolds. So let me now upgrade this example a little bit. So example 2. So now I'll let sigma g, so this is just some surface of genus G. And now suppose I take an element gamma. Well, you can think about it in terms of the mapping class group, but just more explicitly as some isomorphism from this surface to itself. So given such a map, I can construct the following manifold. Namely, I start off by taking the surface and then crossing it with an interval. So now this is a 3-manifold that's just a copy of the surface. And now I want to wind it around, and I want to glue the ends together, but I glue them together using this isomorphism. Okay. So G times 0, I identify using this map gamma with the other end. Okay. So, well, before you take this quotient, this manifold certainly fibers over the unit interval. And when you glue it together, you get this map. It now fibers over the circle. And so now I want to consider the cover, which is just coming from example 1 by simply starting to unwind the circle. Okay. So here's maybe, this is my picture of M. Here. And now, what I can simply do is just start unwinding the circle by maps of degree p. Well, unlike in the previous case, this manifold won't be the same, but you'll sort of get this picture of the following kind. Okay. So this may look actually like a sort of somewhat specific type of construction, having a manifold that fibers over the circle in this way. But it's actually an amazing theorem of Ian Agol that, well, suitably interpreted, almost all 3 manifolds look something close to this. So I can say that more precisely. Well, as long as you take irreducible 3 manifolds, they're almost all hyperbolic. And if you have a hyperbolic 3 manifold, then after passing to some finite cover, it really does fiber over the circle. Okay. So again, here's a sequence of covers. All right, so now let me do another example. I'll skip that one, but something a little bit more arithmetic. So now let me suppose that S is P in infinity, and let QS be the maximal extension of Q unramified at P and at S. Okay. Okay, so now I can let gamma be the Galois group of this extension. So there's some piece of this field that we know quite well. In other words, there are some extensions of Q unramified outside S that are obvious, namely the cyclotomic extensions. So in other words, there's a containment of Q zeta P to the n inside Q of S. And so, well, now, I mean, one could try to write down sort of the objects, but let me just first sort of think about it in a somehow quite formal way in terms of the groups. This group gamma has a natural map to the Galois group of, say, the P, the infinity roots of unity, well, and some kernel, which just formally is the Galois group of zeta P to the infinity, and here's 0. Okay. So in other words, there's also going to be a tower here. Well, what is the tower here? So rather, this group is isomorphic to ZP star. And so inside here, you can consider the group 1 plus P to the n ZP. And then here you have a subgroup, you can call gamma n, with the same kernel, which you can think of, again, if you think about this now as a fundamental group, well, this will now be the fundamental group after you pass to the cover corresponding to this quotient. So if you want to think about this in perhaps a more geometric way, sorry, this is example 3, you could think of this gamma, well, as the fundamental group of, say, Z1 on P. And then this gamma n, well, you can think of as the fundamental group. And so these are the geometric objects, Z1 on P and Z1 on P, Z to P to the n. Okay, so again, here's a tower, of course, in some sense, that's going the other direction, a tower of these fields or these rings of integers, S integers. Okay, so here is a sequence, here are just a few examples of towers. Okay. So I now want to espouse the kind of basic principle one should bear in mind when one is considering towers. So what are the basic principles? Well, the first basic principle is sometimes the entire tower is easier to understand all at once than the objects in finite degrees. So, two principles. So A, well, sometimes, let me upgrade that to often, the entire tower is easier to understand than the individual layers. And B, well, B is in some sense part 2 of the same point, is that this is true even when there does not, well, exist an object at the top of the tower. So I'll leave this vague for now, but I'm going to come back explicitly later. So in some examples, in particular in this example here, which we'll see later, there really is a sort of an object you can imagine being up at the top of the tower, which is just literally what happens when you unwind, well, even in example 1 with the circles, if you unwind all the circles, you get R. Well, of course, maybe I'm only taking powers of P, so things are a little bit different, but there really is a nice universal covering space that you understand. And even here in this example here, you can also start to unwind the circles and then start to see just a copy of your surface with some interval. But in general, for example, in the case of these covers of modular curves, it's not super clear that there really is an object when you take this inverse limit. I mean, you might start to imagine, well, here I'm kind of shrinking the group. Maybe I can just sort of imagine the universal covering space, which is just the hyperbolic upper half plane. But I'll try to explain why this, in some sense, is formally correct, is not going to give you an answer that's sort of useful in terms of understanding the objects. But we won't be able to see that quite yet. Okay. All right, so before we understand towers, I'm going to go even one layer more basic, is just understand a single cover, a single Galois cover, and then try to understand what's going on. Okay. So I just want to take G to be a finite group, and Y to X, well, just some covering map with Galois group G. Of course, there are lots of contexts in which you can sort of think about this, but let's just even imagine we have nice compact manifolds going on here. Okay. So, well, what do we want to do when we understand objects in the tower? Well, we want to understand arithmetic information, geometric information, topological information associated to these objects. So kind of natural thing to look at is to understand the cohomology. All right. So if you have a G cover, how do you relate the cohomology of X to the cohomology of Y? Well, let's just think a little bit about how you compute the cohomology of X. So here we just have a compact manifold, so we're just thinking about usual singular cohomology, or singular homology. Maybe I'll just do homology. So, or I'm going to try to be consistent, which is often don't do. So I've written cohomology, so let's stick with cohomology. So if you try to compute the cohomology of X, well, you might just want to write down, say, some cochain complex, say, of free Z modules. And perhaps even free finitely generated Z modules. So then how do we understand the cohomology of Y? Well, the nice thing if you have a Galois cover is that if you have a triangulation downstairs, you can pull it up to a triangulation here. I say triangulation, maybe I mean sort of CW complex. And here you now get a cochain complex of free Z modules. But if you lift it in the right way, you can lift it somehow in a G equivariant way. And so what you end up here is a cochain complex of free modules, which are actually now modules over the group ring. So free ZG modules. Okay. So, well, let's first, I want to do a basic example. So let's first just imagine maybe that Y and X are curves. And let's even just start with the case in which we're computing cohomology, maybe not over Z, but over Q, just to see what this looks like. Okay. So let's say X is maybe a compact curve. Okay, so we'll say of genus G, let's just imagine the genus is at least 2. So, well, of course, you know how to triangulate a curve. You write down, well, curve of genus 2, you have some octagon which you glue together in some way. So, without sort of explicitly writing down the details, you can imagine sort of a complex of the following shape. So a Q, so I'll say here, genus G, Q to the 2G, and here Q. Well, I said this is a complex. I haven't told you what the maps are, but here the maps are just 0. So the cohomology of this curve, this nice compact curve, it's dimension 1 for H0 and dimension 1 for H2, and dimension 2G in H1. Okay. So now we pull this complex back to Y, and now we have a complex which is just exactly the same, except now we're looking at modules over the group ring. Okay. So again, we should think, I'm thinking in terms of cohomology, we have something like this. And moreover, this complex is related to this one by thinking about the G invariance. Yes. All right, so this complex here is computed the cohomology of Y. Well, it's not, the maps are not going to be 0 here. On the other hand, the cover will certainly also be another curve. And we know what H0 and H2 of a curve are. So we know the cohomology in this degree should be Q, and the cohomology in this degree is Q. So just from this computation, we can automatically deduce something about the cohomology of Y. Well, let me write it in the following way. So it's equal to, I hope I get this right, okay, I'm writing this. So I'm thinking about it now in terms of the Grothendieck group. So 2G minus 2 times QG plus 2Q. I hope I did not get any signs right. This is just in the Grothendieck group of representations of G. So in other words, well, since you know the cohomology here and here, that's enough in the Grothendieck group to compute the cohomology of the rest, and you get an identification here. So just by a completely elementary argument, of course, you've probably seen this argument in a very similar flavor before, which is namely comparing Euler characteristic here and Euler characteristic here, and then you compute what the genus of the curve is in terms of the degree. This is in some sense the same argument plus epsilon, where you try and keep in check of the action of the group as well. Okay. So this is kind of basic. And more generally, what we find, well, if we try to compute the cohomology of x and the cohomology of y, well, this is maybe not, generally is not quite the right word, but one thing that we can certainly deduce is that the cohomology of x, well, I'll put a Q here, is just going to be the cohomology of y, where we take G invariance. Okay. So in other words, we have an action of the group upstairs, and what you can do, you can think about it in terms of this complex, you can think about it in other ways, is that if you have a class upstairs, you can average it over this group. You can sort of sum over the elements of the group G, you can divide, and then you have an invariant class that will have to come from here. Okay. But this is something that sort of starts to fail quite poorly when we start thinking about integral cohomology. So this is a reflection of the fact that when we have finite groups acting on complex or vector spaces in characteristic 0, the representation theory is all semi-simple, and so we have something sort of fairly elementary. So the question is, well, what happens with coefficients, say, over Z, or maybe more generally, over A for some coefficient ring? Okay, so how should we think about this? Well, what are we doing? There are somehow two types of operations here. We have this chain complex, and if we're trying to compute the cohomology of x, we could try to think about first taking the cohomology of y, somehow taking invariance and then taking cohomology, and then maybe comparing that with taking cohomology and taking then coinvariance. So we have these functors that we're trying to sort of understand how they are maybe composed. And usually what happens, if those functors are not exact, that you end up with a spectral sequence. So I want to just write down the spectral sequence relating the integral cohomology of these things, and then give a very concrete example of what one can deduce from these kind of things. Okay. All right. So I'm still in the same setting. I have y mapping to x, some Galois cover with Galois group G for some finite group G. And A is some coefficient ring, which you could think of as Z or as FP. More generally, it doesn't matter so much. So y to x. Galois with Galois group G. Right, so what do we want? What are we thinking about? So we take the cohomology upstairs with cohomology in the ring A, and then we somehow want to take, well, not just the G invariance, but maybe the derived invariance. So in other words, the group, I have switched to homology at this point. Okay. Right, so of course, and homology maps are going the other direction, you instead want to take the co-invariance instead. So of course, H0 is the co-invariance. Okay. Sometimes homology is nice. So this is going to map to the cohomology of here. Okay. So for example, if A is a field of characteristic equals 0, or even just more generally, if G is invertible in A, well, then you know the higher cohomology of a group vanishes. So if the higher cohomology of the group vanishes, all these terms basically disappear except for H0, and then you're just left with, well, H0 is just the co-invariance, so then you would just have this formula here. Next thing. Okay. So it might seem a kind of a terrible thing that when you think about the integral story, you don't get a formula that's nice as this. But, I mean, every cloud has a silver lining. I mean, what is it that means that there's a failure of this kind of relation? Well, one way to think about it is the fact that when you have an integral structure, you can start talking about congruences. Right? Things are congruent if their difference is maybe divisible by p in homology. I mean, of course, in characteristic 0, everything is divisible by p. And the failure somehow of this sequence, just to kind of give you something very silly, is that in some way, these different cohomology groups are recording congruences between different forms. And these congruences are usually very interesting. And so even though, of course, we've lost a kind of simple formula, it's reflective of the fact that the integral cohomology contains some sort of deeper data. All right. So I just want to do one very explicit example. I mean, spectral sequences are the type of thing that are very complicated until you understand them, and then they're very easy. Maybe that's true of many things in mathematics, but I just want to kind of give an example to kind of see what one can extract from these kind of computations. So again, this example is a very algebraic topology type of example, but in some sense, and of course these things are true more generally if you start taking kind of Galois covers of say, suitably nice varieties in the appropriate sense, you have the similar type of sequence with the appropriate kind of cohomology. All right, so here y, I'm just going to let be the 3-sphere. And x, well, I want it to be a cover, so I'm going to imagine it's the 3-sphere modulo some group G. Well, here G is acting as some nice way, so somehow no fixed points. Okay. And I'm going to give some more information. Well, of course, I know what the cohomology of y is. It's the cohomology of the 3-sphere. But I'm also going to tell you what the cohomology of x is as well. So I'm going to imagine that these are both just z when I is 0 and 3 and 0 else. Well, we certainly know that's true of the 3-sphere. So essentially what I'm saying is here I have a quotient of the 3-sphere that's a homology 3-sphere. Okay. So, well, here I'm kind of using this in reverse. Now I tell you what the cohomology is. Can you say something about the group G? Well, of course, it could be trivial, and everything would be correct. But what else can we say about it? Well, we have this spectral sequence here, and because the cohomology of y is somehow 0 most of the time, the spectral sequence is fairly simple. So what do we have in the corner? So, well, what do we have along this row? We have the group homology of just H0, YZ. Good, I said homology here. So, well, one remark here. So how does the group act on Z? Well, there are not many actions of a group on Z. It can kind of act bitrivially or by plus or minus 1. But if we did this rationally, if it acted, say, on H3 by minus 1, then that class would have to disappear in characteristic 0. And so since it doesn't, we in fact know that not only this group G is really acting trivially on all these cohomology groups. So we have the simplest situation. We know everything here. We know everything here. We know this. We don't know the group, but we know it's acting trivially. So here we have a Z. Here we have H1 of this. So here we have H1 of GZ, H2 of GZ, H3 of GZ, etc. Okay, and now there's no cohomology of y in degree 1. There's no cohomology of y in degree 2. And now here we have H3 of yz. Again, that's just z. And as I just explained, when you take the cohomology, well, we just have the active group is acting trivially, so there are no, the co-invariants are just everything. So here we have this, H1 of GZ, H2 of GZ, H3 of GZ, etc. All right, so what do we have? We have, this is the page 2. We have a story like this. And we know what the answer is in terms of the spectral sequence. We have to end up with a Z in this degree. That's already automatic from here. And then here this has to vanish. Here this has to vanish. And the spectral sequence here, we have to get a Z in the end. And then everything else has to vanish. OK. So, well, what are the initial maps here? on page 2 we have these maps, and there's really nothing interesting going on because all the maps are between objects, at least one of which is 0. So somehow nothing happens on page 2. So we flip the page and go on to the next page. So what do we start to see? Well, already these terms here, there's nothing in these terms that can change them. I mean, this is already fixed for all time here. This is mapping to 0, and it's fixed for all time here. So that means these have to occur in the limit. But we said the cohomology of x was trivial, so this has to disappear, and this has to disappear. So we've now deduced something about the group G just by this fairly formal computation. Namely, first we've deduced that the group is perfect. So we've deduced first that H1 GZ is 0, so here G is perfect. And then we've deduced that H2 of GZ is also 0. So has trivial Schur multiplier. Okay. All right, so now we have the next point, and so now we start to have something a little bit more interesting. So we have this. Well, again, this term here is fixed for all time. Okay, but this Z is going to receive now here a map from H4 GZ. So what is this last term that we get? Well, let me write it out. Here I get it the right way. So we're going to have, we'll have H3 of GZ. Then this next term here will be H3 of XZ. So we know this is Z. Then the next term here, well, that's going to be this Z here. And let me now write it in terms of what it actually is. It's H3 of YZ invariance, which of course we know is Z. And then mapping into this is H4 GZ. So this is what we extract by looking at this term. So what can we see when we look at these terms here? Well, now we have to think about this not completely formally, but think about it a little bit geometrically. We're just looking at the fundamental class of y mapping to the fundamental class of x. This is just the degree. So that means that this group has to be isomorphic to z mod nz, where n is the degree. Well, that's just the order of the group G. What about this? Well, we know it's a finite group, and we know it's a submodule of Z. So we deduce that this is equal to 0. Okay. So, of course, we could continue this on. And let me just sort of give the answer. So what's the cohomology of the group G? So it's Z if the star is equal to 0. It's Z mod nz if the degree is equal to 4k plus 3, and it's 0 otherwise. So we can just formally extract this from this computation. Okay, so say you're trying to understand all quotients, all somehow integral homology spheres to the quotient of the 3 spheres. You've reduced your problem, or reduced, or at least translated your problem, to now understanding groups which have some certain cohomology property. So of course we know that there is an example of a group with this behavior, namely if you take G to be the unique degree 2 central extension of A5. That's certainly a perfect group with trivial Schur multiplier. And this is the cohomology here with n plus 120. Well, and as I mentioned before, G is equal to 1 with n is equal to 1. Okay. So let me just leave here. Here's an exercise. Just using this same argument and some facts about the cohomology of groups, you can prove that Sn has a quotient by a finite group G that's non-trivial which is a homology sphere if and only if, well, I guess 0, 1, or 3. Okay. So I'll give it a hint. Not sure if this is a hint or not, by somehow saying this certainly follows from result of Swan. Okay. All right, so this is just a purely kind of topological type of computation, but I just want to start to say, here we're just using really basic tools from algebraic topology. Right? We're in this situation in which we start to try to understand, well, not just the cohomology of Shimura varieties, but the cohomology of more complicated Shimura manifolds that have no algebraic structure. And so not only does it have no algebraic structure, if you're interested in the cohomology of finite fields, there's no de Rham cohomology either. So you basically have nothing. You're starting from the beginning. And so you have to start to say, well, what can I say by completely elementary tools? Okay. All right, so here I talked a little bit about one step up the tower. Now I want to start to talk about why you might consider the entire tower rather than just one tower at once. Okay. Okay. Well, so again, y to x with Galois group is G. So what we certainly have is that this cohomology of y, well, in some ring has an action of G, so it's a module for the ring AG. So I want to talk about a fundamental example of this kind of picture that I hope will illustrate something which we should think about. So let me now just take A to be ZP. FP would also be similar, but say ZP. And let me take the group just to be the cyclic group of order P. Okay. So now this cohomology has an action of this group, well, the group ring of Z mod PZ, which is just ZPX on x to the p minus 1. Okay. Well, let me even anticipate where we're heading, put an extra factor of k here, and put an extra factor of k here. Okay. So what's going wrong by having ZP instead of QP, as I mentioned before, is if you just had QP or you just had C, this algebra here just breaks up completely into its irreducible representations. And so that's nice and simple, but the bad thing is that all these representations do not talk to each other. If you know what the cohomology at one character is, you don't know anything about the cohomology at another character. But this ring here has a very nice property, which is that, namely, in characteristic 0, if you look at the generic fiber, it just splits off into completely distinct characters. But if you reduce this mod p, well, if you reduce this mod p, you get fpx modulo x to the p to the k minus 1, which is just isomorphic if you let t be x minus 1 to fpt modulo t to the p to the k. So in other words, in characteristic 0, this breaks up, but in characteristic p, it's connected. And this exactly means that even if you're only interested in objects in characteristic 0, if they're somehow related in terms of p groups, and you're interested in congruences mod p, there's information being transferred from one character to the other by reducing mod p and thinking about them in terms of congruences. Okay. So, this is used a lot in many somehow situations. I don't want to kind of give them now, but it's sometimes a very stupid observation, a key kind of technique in lots of situations. So that's one nice thing about this ring here, is that it has this property in that it's communicating information between different characters by using congruences. But there's also a bad property of this ring here. So this ring, even for k is equal to 1, this ring is not a domain. There are zero divisors. X minus 1 is a zero divisor. If we're interested in understanding modules over this ring, the module theory of this ring is not so great. It has infinite cohomological dimension. Right? We were sort of nicely going along trying to understand kind of the cohomology of these manifolds, which maybe only have cohomology infinitely many degrees, you start writing down the spectral sequence, and the spectral sequence is really going on infinitely long. So, well, of course, in some sense, I mean, not always, but this is in some sense a bad property of this ring. So, well, how can we somehow preserve the nice property about the congruences, but eliminate the bad property that this ring does not have nice properties as a module? Well, this is exactly where we can now pass to a tower. So in a situation where you have a tower, well, it's not necessarily the case that there's a nice geometric object at the top of the tower. But on the other hand, it still in some sense makes sense to talk about the cohomology of the top of the tower, namely of the cohomology at finite levels, and you take a limit, or the homology at finite levels, and you take a direct limit. So let's just now somehow imagine, again, a kind of formal system of covers such that here the Galois group here was z mod p to the nz. So if you look, for example, at the homology of, say, Mn with coefficients in P, it now has an action of this group, Zp z mod p to the nz. Is that better? Okay. All right. So now what you can do is, for example, you can take the inverse limit of these groups, n. So what does this now have an action of? It has an action of the inverse limit of this group. So, well, of course, formally, it has an action of Zp, just the group ring over Zp. But if you see how that group is acting, that is acting, I mean, open subgroups are acting trivially on each finite quotient. So you get something much better. You get an action of the completed group ring. So Zp double brackets Zp. So this is just, well, this is isomorphic, which is just a power series ring in one variable here, where T you can imagine is 1 as a generator here, minus 1. I think that's correct. Okay. And so now this ring, it has all the benefits that this finite ring had without any of the deficits. This is now a very nice, I mean, it's a regular local ring of dimension 2. You know a lot about the modules over this ring. And now you can start to say, well, how can I understand this as a module over this ring? And now you can start to bring into play, for example, information about just the module structure of this ring. Okay. So let me do an example. And this is an example in some sense. You'll say, well, this is a silly example, but I still want to talk about it. So let's again go back to my 3 manifold that's fibering over the circle. Okay? And again, now what I want to look at is just the inverse limit of the first homology of all these covers with coefficients in Zp. So this will now be some module over this completed group ring, and the question is, what can you say about it? Well, the reason this is a silly example is that there's really perhaps a more sensible way of doing this computation, simply because you really can just unwind all the circles at once and get a nice object at the top that's fairly simple, which you can compute with. So let me first just do it in that simpler way, just so we know what's going on. Okay. So this is not exactly this, but it's something similar. So what, of course, we can do is ignoring the powers of p and just really pulling everything back completely. If we sort of just unwind the circle completely, we just get the surface by some interval here. And of course, we can just compute the cohomology of this object here. Compute the homology as well. The first homology is just the first homology of this, which is just z to the 2g. Okay. On the other hand, of course, we have a cover of M by Z. And so there are deck transformations. This Z is acting on this picture. I mean, how is it acting? Of course, it's just translating across by 1. But what does that mean in terms of the action of cohomology? So we have this action of this group ring. It's not a completed group ring now. It's just literally the group ring of the integers, which is not ZT, but yes, that's probably a bad choice of T. Maybe I'll call X. That's a better choice of letter. Okay. Hope you can read that. So here, X is acting. Well, how is it acting? Well, it's exactly how we glued it together. It's exacting X is acting through, well, we had this isomorphism of the curves, and that induces some map on homology. Okay. Well, so it's not really any surprise what we're going to get in this picture here. What we're going to get is just now ZP to the 2g, and now we'll have an action of ZP t. And, well, you can imagine t is really this minus 1. So now 1 plus t is acting on this via this element here. So you really get, in some sense, the same thing. Well, here we've kind of tensored with ZP. We have this. All right. So in both these pictures, well, how do we use the module theory of these rings to extract more information? So one thing that's kind of nice is this ring is actually not quite so bad. I mean, of course, QX, X inverse is a PID. We have some Z. We have to worry a little bit about denominators, but it's not so bad. What type of things can you do with such modules? Well, as long as these modules are somehow maybe torsion, I mean, even if they're not. I mean, of course, if you have a PID, what do? You just take the product of the elementary divisors, and you have the order of some group. But here we have something that's kind of one dimension higher up, but you can take something which is called a fitting ideal. Namely, this is pretty close. Modules over these rings are pretty close to a kind of direct sum of cyclic things. And you take the corresponding product of the things you quotient out by, and you get some ideal here, which you can turn out just, well, some ideal, really some number, which you can call AX here, or maybe here AT, which is just an element of this ring. And what is it? It's the Alexander polynomial of this cover. So this is sort of geometrically and topologically a kind of well understood type of element. Well, here, I mean, of course, it's just exactly the same element. So this is maybe probably a bad example to say to convince you why you should sort of look at this type of cover.
So this, when you say the Alexander polynomial, if you think in terms of modules over Iwasawa algebras, it's just the characteristic.
Exactly. It's exactly that, yeah. So, I mean, in some sense, this even tells you a little bit less information, because here you know it's a polynomial. Here you maybe have a power series. But still, I want to say that formally what this computation is doing is producing a kind of Alexander-type polynomial object associated to this tau.
No, but you will get a polynomial if you just take the distinguished polynomials, right?
I mean, well, I mean, of course, there's an ambiguity exactly up to units. Yeah. And it's not sort of super clear how canonical. Up to units. So, well, maybe you're even okay. All right. All right, so here that's maybe not a good example to sort of convince you that this is what we should be doing. But now let's go back to the case of modular curves. Say x1, xp. Well, again, you can do both type of things at once. So what happens if you try to do this construction here? Well, what will happen, I mean, of course, you could, in some sense, just pull back to the universal cover, and you'll end up with modules. I mean, you can pull back a triangulation all at once, and you get modules, well, of course, essentially over the group PSL2Z. Now, in fact, this is not completely hopeless. Right? What happens if you take a triangulation here and then pull it back and start to sort of work out something here? Well, you'll get some complex. You try to compute exactly what it means to take the cohomology at various levels. If you work that out carefully, you'll rediscover modular symbols. All right? On the other hand, this is a terrible ring. Right? It has no nice properties at all. I mean, here you somehow just are amazingly lucky that the group ring of Z happens to actually have a nice properties. This ring here is terrible. On the other hand, if we complete in this p-adic way, you'll get a ring which will now be the completed group ring. Well, of course, now, well, of course, we may be taking the disconnected part, so we sort of allow ourselves a GL2, but you can do SL2. Well, maybe I'll just stick with SL2 here. You'll get a module over this completed group ring here, and this is somehow a ring with much nicer properties. Right? So somehow here, this is a ring that basically, well, of course, it's non-commutative, but it's pretty much as good a ring as you could hope for in that situation, in the sense of it being analogous to here. I mean, this ring here is regular, it's local, it has this nice properties in terms of cohomological dimension. This ring, in some sense, has the same property. Well, you have to maybe be a little bit careful about the sort of the prime to p part, and maybe some torsion elements that are somehow, maybe you want to replace this, but it's sort of the p congruent subgroup. This is somehow a ring with much nicer properties, which is sort of analogous to this. So, of course, moreover, you have an action not just of SL2ZP, but GL2, but SL2QP. And, of course, that's the Hecker symmetry here. That was already, in some sense, maybe a justification for going up the towers. But here you have some kind of control that allows you some sort of cohomological understanding of what's going on. Okay. So, really, the objects that you sort of study here, there's not really a way you can get it simply by unwinding things geometrically. You have to actually sort of really just work with the cohomology in some formal way of completing this. Okay. Well, of course, I say that, but in some sense, one of the kind of remarkable things to come out of Peter Schultz's work is that, at least in the context of Shimura varieties, you can really start to put an object which is actually giving you something here at the top of the tower. Not in a kind of the most general situation, but at least in the context of Shimura varieties, where one has a bit more extra information. Okay. So I think in some sense I've finished today, but I just want to give one statement just to kind of allude to the type of problem that one may want to think about in terms of tau. So now let's again just go back to the case of modular curves. Well, no, rather not modular curves. Let's suppose that we actually have, say, SLNZ. Okay, well, maybe we'll call this gamma n. And gamma n, p to the k, is the congruent subgroup. Okay. So what we can do, for example, is we could take the cohomology here, and let's now look at FP coefficients. And now let's take this direct limit. So again, for cohomology, you want to take direct limits. Homology, you want to take inverse limits. These things are analogous, but it's just like in the case of Iwasawa theory, you have compact things and discrete things. So this is really more a discrete thing, a co-compact thing. And here you have an action. Now say, well, if you have to do it a little bit, let me just say this for now, but if you kind of do it with components, you get the kind of the right GL2 action. So I just want to make some observations. I want to think about d is equal to 1, or maybe d is equal to 2. And let's suppose that n is very large. So in Birgit's talk, we somehow already saw what was going to happen here. Well, let's kind of ignoring issues to do with compactness. In characteristic 0, when you look at the contributions to cohomology, well, you get just the GK cohomology of automorphic forms. But most of the time, the GK cohomology in low degree is going to be 0. And in fact, you know that once n is big enough, the only thing that's contributing to cohomology here in characteristic 0 is the trivial representation. And just as it happens for SLN, the degrees in which the trivial representation contributes in high degree starts in degree 5. And so in particular, if you do this computation in characteristic 0, as long as n is big enough, this will just always be 0. But now even for example, for H1, which just seems like a very simple thing related to group theory, you might struggle to sort of think about what is this object and what is the action here. And the problem is there are sort of two things to overcome. The first thing to overcome is, well, do you understand what, say, smooth admissible modules of a GLN of FP of GLN QP are? That already, as we see maybe in Rachel's talks, is a sort of very difficult problem. But even if you overcame this problem, the difficulty is there's no analysis to tell you, well, this representation, if it will occur, and this representation will not. So this is sort of a problem that is coming from the fact that cohomology of FP has no direct relation to automorphic forms. So you might say, well, I'm only interested in automorphic forms because they're associated to Gauss representations. But you'll learn pretty quickly that if you want to understand Gauss representations, you want to reduce them mod P, and then you want to understand Serre's conjecture, and then you start to run into problems that maybe things in characteristic P don't lift. Okay, so I'll talk more about arithmetic groups next time. Sorry for going over time.